Okay, good morning. I posted, I'm kind of trying something new for me, maybe not for you, where I took my notes from last year and instead of kind of grabbing these things and bringing them in class, so that takes some time. So these little excerpts are just from the textbook, but also from something I don't think I have made available. Oh, no, I have the chapter 1 examples. So, I just want to view it. So the chapter 1, chapter 2 examples is just going to be kind of a slide deck of examples that we're going to work through. And so that's where I'm pulling these from. So if you're wondering where did these come from, there, looks like the first slide in that slide deck, I hope. And so that's just where they're coming from. But in general, I'm just snagging definitions and things like that so we don't have to write them out, or I don't have to write them out by hand. So they'll be kind of in there. We'll see if the spacing is okay. Like I said, this is the first time I'm kind of doing something like this, so we'll see. Okay. So, any questions about last day before we start? All good? Emily, we didn't do anything last day. I know. That's okay. Oh, yeah. I posted the solutions. Okay. There are a couple of questions. Probably I didn't make note of all of them, but when there were a lot of different ways that you could approach solving the problem, I did make a note, right, just so you're not thrown off by how I did it, right? But we are going to be working with kind of exponent laws and things like that later, and so might be nice to try it, but we will be working through all these things. Yeah, same thing with simplifying fractions. As long as you have a common denominator somehow, then you're good.
Speaking of this test, actually, could you go up a little bit?
Yes.
There's a question I was kind of confused on.
Okay. Stop me when you.
That's it. Yeah, I think we probably did.
Passed it. It's like conversions.
It's the one where you have to simplify the x's.
So
it's an easier x thing.
Yeah, probably this one, right? Yeah.
A. I thought when you're feeding the chickens, you would have to times the x by the 4x. Wouldn't that make 4x squared?
So this, do you mean this x?
Yeah.
So then here, this x is being added to 2, but 2 is being multiplied. So 2 is going to get fed in.
Oh.
But the x is going to be added.
Okay.
Yeah.
Cool.
Nice. Awesome. So you've got the very stressful diagnostic test that we didn't do in the orientation week. Aren't you so grateful? All right. So, like I mentioned, we're going to start from kind of ground zero, basically. Not ground 0, 0, 0, but kind of at a very basic level of pre-calculus. And so if you're not 100% on your math skills, don't worry, we're gonna take it nice and slow. And like I said, if you're up top on your math skills, then you can probably sleep in. Okay, so chapter 1 is on functions. We're going to kind of run through some properties of functions, things we can do with functions. We're going to be working with functions throughout the term. It gets a little bit strange because we kind of introduce these concepts and then we go back to the beginning in chapter 2 and kind of start with lines, and then we move on to kind of higher powers. But we introduce all these concepts in chapter 1. So first things first, what's a function? Function takes some input and produces some output. Reasonable enough. And so it's a rule for a relationship between input or independent quantity and an output, or dependent because it depends on the input, right? And so here, I don't tend to call them the independent and dependents, but it might be helpful because it depends, on the input. For example, now I'm trying very, very hard to avoid function notation until later, but it's very difficult for me. We're going to have kind of shorthand notation, right? For example, the age, the height of a child depends on the age, right? Typically, or that's a reasonable relationship, right? So if I tell you, oh, this child, why am I not saying this person? Well, because knowing that I'm 38 years old doesn't tell you anything about my height, right? Kind of stops. But for a short amount of time, we have a pretty strong linear relationship. And so the height of a child depends on their age. Of course, there are I'm generalizing. That's one of the kind of a reasonable example. So what would that look like? You might have, your y-axis, your x-axis, right? You have their height and their age, right? You got your height on the y-axis and your age on the x-axis, okay? Then you might have something like a relationship like this. I'm not going to spend time putting in ages and things like that, but we understand that you start some height and then you keep growing. It's pretty rare that you digress. And so Benjamin Button style, I guess. Right, but in general, and of course there are kind of going to be data points around this, but in general, this is the relationship. How can we describe the relationship of a straight line? You might, if you think back, remember something like y equals mx plus b. Oh, that sounds kind of familiar. Why does that sound familiar? Y equals mx plus b, or ax plus b, or b plus ax, or some combination of that. But typically in high school, they tend to use y equals mx plus b to communicate a line, right, with a slope. And so here, this is the equation of a straight line. Where m, so whatever is attached to the x, is the slope. I'll start over here. Where m, or I guess I shouldn't say whatever in my notes, or the variable attached to the x is the slope and B or whatever is alone. Again, I guess I shouldn't say whatever. And B, the variable, I'll put alone in quotes because that's kind of a, I don't know, I think we understand, but it's not a mathematical term. And so the variable alone is the y-intercept, right? That's gonna be where it crosses the y-axis, which means what? Means that x must be 0. Okay. Like I said, we kind of introduce all these things, but then in chapter 2, we're going to spend the entire chapter talking about lines. Okay, so straight lines. So we're going to come back to this and kind of fill in some gaps. But for us today, this is a function, right? The output y depends on the input x, right? Whatever I put into x here will dictate what the y is. Okay. And so here, if we have y equals mx plus b, then this is the output. So y is the output and x is the input. And then from above, m is the slope and b is the y-intercept, or often I just drop it because we never really care about the x-intercept. So when I say intercept, it's the y-intercept. And I would specify if I meant the x-intercept. Okay. Okie dokie. So this is one of our first functions that we're going to be dealing with. Okay. And so one of the key things about a function is that each input value uniquely determines one output value. Okay. And so that's what makes a function. Okay. That can look like, so here, if we consider a function, I'm going to try to keep it on one page. So here, traditionally, when we talk about functions, we use these kind of set spaces, just use kind of ovals to indicate just output, input numbers. And so if we have kind of 3 different inputs here, right, then they have to map to, right, each input value uniquely determines one output value. So what does that look like? If it's a function, then we could have something like this. We're allowed to have just 2 possible outputs, but this value goes to one thing. Maybe this also goes to the same output, right? But it goes to a unique output. And maybe this little guy goes to that bottom one. Okay. What would not a function look like? Nice. Perfect. I was going to reuse my my things, but I'll just scribble it down. So not a function, I'll do it in red, would be if you had this little guy mapping to 2 things, right? It has to go to some unique output. So this is the bad part. But like I said, you're allowed to have 2 inputs going to the same output. That's still a function, but if you have 1 input yielding 2 possible outputs, that's not a function. You can still work with that, but it's not going to be a function. Okay. Any questions so far? Is this relationship a function? We've got student ID numbers, so I can put in some student ID number and figure out what their 11 a.m. class is. Okay. So is ID number a function of the 11 a.m. class?
No.
No, right? Because I could say, oh, an 11 a.m. class produces many student numbers, right, in this 11 a.m. class. So, huh? 11 a.m. Oh, it's just that. No. Since the 11 a.m. class will produce more than one student number. Hopefully. Is the 11 a.m. class a function of ID number? Yes, right? Because you can only be in one class at a time. And so if I input the ID number, then there will be a unique output of where you would be at 11 a.m. Okay. So yes. Since a student, I guess ID number can only be in one 11 a.m. class, I guess at a time or something like that. But just to show kind of what's a function and what's not a function. How about a special function, a one-to-one function? So sometimes each input corresponds to exactly one output, and then going back the other way, it's the same, right? And every output corresponds to exactly one input. Okay. This is called a one-to-one function. So each input corresponds to exactly one output. And every output corresponds to exactly one input. I'd have to have the same number of inputs, outputs, right? Because I'm gonna have something, I'll just do them straight across for simplicity. Right. Each input corresponds to exactly one output. That's good. Kind of moving from input to output, but also every output corresponds to exactly one input. So moving the other way. This is a special case of a function, right? And so it's a one-to-one function, and we use one-to-one functions to move back and forth, right, from input to output. But that only works if we have this one-to-one function. Questions so far? Where am I? Just waking up.
Would this function be a lot like the function that you wrote down at the start where mx plus b equals y?
Mm-hmm.
Okay.
Nice. So here, if we go back to our straight line, we can think about, so here on this axis, I can draw up and give it some input, and then the output would map to some place on the y-axis, right? And so some output. And because I can do that uniquely, right, going either direction, this is a one-to-one function. Nice.
Is there any other types of one-to-one functions?
Yeah. What a great segue. I've got, well, okay, on the okay, I've got a shortcut for figuring out if it's one-to-one. We'll have a look. We'll have a look at some examples. But first I need to introduce function notation because it's been painful, so painful. Let's see here. I'll put this here. So, of course, in math, we introduce notation, shorthand notation, mostly because it gets pretty wordy if you actually wrote it out. And so rather than writing height is a function of age, we could use the variable h, right, to represent height. And we could use the descriptive or the variable a to represent age, perfectly reasonable. And so what we could do is we could start with height as a function of age. Okay. Now, what we do is we name this function f, and that's where a lot of people kind of stop listening because, right, it's been a while maybe. And so if we replace all these shorthands, right, with, let's see here, h is a f of a, right? That's okay. I've just replaced height with h and function with f and a with, or age with a, right? And so still saying the same thing. So then h is f of a, still saying the same thing. I've just dropped a function. Okay. And then we make this jump, right? H is equal to f of a. So whenever you see these brackets here, you're going to read it as of. Okay? And so here, this is f of a function of a. Okay? Or we could rewrite it as h of a, right? Height is a function of age. Most commonly, right, we've already seen y equals mx plus b. Usually what we do is we don't write y, we usually write f of x, right? And so, or f of x is mx plus b, right? A function of x is the slope times x plus b, right? I manipulate my input and I get the output f of x. Okay. It took me, so I did my undergrad in math, my master's in stats. And so everyone's kind of like, oh, well, you must be like really good at math or something. And no, I wouldn't say I was that great at math. I really enjoyed it and I didn't mind working at it. And so there are a couple of things that I think some people might not have struggled with, but the day that I realized that if you see f of x, you can just write y, and it's okay, they're the same. That was like a huge light bulb moment for me. And so I was like, oh, okay, bless you. If I see f of x, you can just ignore that. You can just write y. That's cool. Nice. Now I've kind of, that was like in high school, but it was a big light bulb moment for me. Okay. And so, because this felt really scary, and the f of x, I don't really get it. I get that it's a function of x, and I know how to read it, and I get it. But when I realized that you can just write y instead, if that's helpful to you, then it was kind of off to the races. Okay. And so when we write f of x, right, that's just the output. And so we mean the output which you could just replace with y if you find that that's helpful. Maybe not. Maybe you guys are all think you're better than me. Yeah, probably. A lot of people are. But I don't know. I think it's why I like teaching these courses, is because I kind of get it. It's hard. Okay. So we're going to be using function notation, though, a lot of it, just because it is a nice shorthand for us to have. And the more we see it, the more we work with it, the more comfortable we'll be. And eventually you won't even think about it. So here, function notation looks like this. So we have this output, let's say y, right, is f of the input. Okay? And so generically we call a function f, but if we have kind of a name for our function, we might use another variable. It's totally fine. And so the output is f of input, right? So here, when you see this kind of brackets, you're going to read it as f of input. For example, if you have a function, some function that takes the input holiday and then returns the month that the holiday is in, right? Then this is going to, nope. You guys can't see the pencil choices, but sometimes I press something completely wrong here. Input, and then the output of the function, right, is the month that it's in. Before we do this, I want to kind of call attention to these two words. Notice that they're different. Okay, so for now, we'll kind of parking lot that, but just pay attention to those two word choices. Okay. If we have to evaluate f of Halloween, I would return October, right? What am I doing here? If I have to think about, okay, so solving evaluating looks like, okay, I give my function some input and I evaluate the output, right? And so here, let's kind of take a step back here. And so I give my function an input and evaluate the output. Solve f of x is equal to November. What's it asking us to do there? Probably figure out what the input is that generates November. We have Remembrance Day, which I never really know how to spell. But, right. So solve for the input X that generates the output November. Solve for the input, I'll put in brackets X, that generates the output, which in this case is November. X would then be my input, right? Generically my input. So X is, let's say, Remembrance Day. Remembrance Day. I guess at the Apple launch, in the notes, I think it is, or I think maybe they linked up with Notability where it kind of auto corrects and cleans up your writing. So I can't wait for that because wow, game changer. Whenever I'm writing, I'm always waiting for the little red squiggle. Like, oh, we'll see. I'll just play it out and see what happens. Well, it's not coming. Well, it turns out it is coming and I can't wait.
Misspelled it.
But I made it nondescript. Yeah, Remembrance Day. Or as my mom calls it, Novembrance Day. Because she can't keep it. She's ESL, so she gets a pass. But yeah, she can never keep track. But she knows it's in November and it's something Remembrance Day. Which is pretty funny because both my husband and my sister are in the military. So kind of a big thing. But she still calls it Novembrance Day. How about this? C of P, right? So we're gonna get comfortable just reading functions like this. So C of P gives the cost of grooming a poodle weighing P pounds. Okay. Only poodles, I guess. That's okay. And so we've got, what's the output? Output must be the cost, right? And so let's see here. The output is the cost because the input is the weight in pounds. Less. If that's the case, how would we interpret C of 20 equals 30? The cost of grooming a poodle that weighs 20 pounds must be $30. Right? And so here, C of 20 equals 30 means the cost of grooming a poodle. It's specific to poodles, so I have to say it, I guess. A poodle weighing 20 pounds is $30. Right? 20 is my input and 30 is my output. Okay. Any questions about function notation or anything? So I kind of highlighted the difference between solving and evaluating functions already. You don't have to memorize what they mean because it'll be kind of obvious from the question, right? And so if we scroll back up here, right, we didn't need to know the difference between evaluate and solve in this case. We just kind of figured out what we had to do, right? And so evaluating meant, okay, I'm given some input, I should probably give the output, right? Whereas when it said solve f of x is equal to November, it was kind of prompting us to solve for x, right? That gives the output November. I'm trying to remember what the American holiday is. Thanksgiving in November for the States, right?
Isn't that any Thanksgiving like Pilgrim's Day?
Yeah, they have it like late November, right? I think. Unlike us, for some reason, we have different Thanksgivings, but American Thanksgiving is like right before Christmas. It's crazy. They just holiday.
This is same dinner twice too.
We do have September,
We do.
which is often a interesting holiday month.
That's the fourth Thursday in November.
Crazy. Oh, it's one of those moving ones, I guess. Or not really. Yeah.
I just remember when I was in school, like you would never have a full week in September. When I was in high school, it was just like holiday. Oh, and a couple years back there was the Queen's Death, which was a holiday as well. Which fair. It is. That's so young though. Yeah, she was expected to have another like 300 years.
That's true. She is the queen. So if anyone can do it, it's her.
Exactly.
Well, not anymore.
Or she was the queen.
Probably not gonna do it now.
No. Well, who knows what those guys are up to?
Yep.
So like we were saying, when we're evaluating, we know the input and then we use the function to find the output. Okay. And so let's see here. One of the other things I want to highlight is that evaluating will only produce one result because it's a function, right? And so we said each input can only yield one possible output. That's what makes it a function, right? And so whereas solving equations is when we know the output, I guess I should highlight it just, and we use the function to determine the inputs, potentially more than one, right? And so notice that, oh, I guess I'll just highlight it here. Solving a function could produce more than one solution, since different inputs can produce the same output. I'm tempted to move away from the my little ovals for the function. How about we take it up a notch? got my X and my Y axis. Parabola. Fun to see. Fun to do. Okay. So here, this is called a parabola, which typically has f of x is equal to x squared. Right? That's the generic form of a parabola, is when the highest power of x is 2. Okay. And so I could give it some input 2, right? Some x input 2, and it would produce some y output of 4, right? 2 squared is 4. Nice. So each input yields its own output. But what if I try to take it back? I shouldn't do it in red. We can still move this way. Let's say that's 4. So if I'm trying to move from some output and trying to solve for that value of x, right? This is a function, but we're not going to have some unique output. It's not one-to-one, right? And so it's okay. We'll be able to solve for these things, right? Because what happens, and I used to love to forget this, so if I write y equals x squared for simplicity, right, but also kind of smudging the f of x and making it y, right? If I have to solve for x, then what would I do? I would take the square root of both sides. And so the square root of y is the square root of x squared. What am I forgetting? The plus and the minus. I always forget the plus minus. Not anymore, but I used to. Right? Ah, what's the big deal? You can just use the positive version, and usually you can. But we have to recognize that it will yield 2 solutions, right? Plus and minus. What the? Okay. So plus minus the root of y is equal to since I've got the plus minus on the root of y, I can just say it's x. You could say plus minus, but you don't have to. All right. Okay. X is, well, let's talk about the square root of 4 for a second. Square root of 4 is 2, but plus minus 2, right? As we can see here, plus 2 and minus 2. Right. Nice. So solving tends to be a little bit more involved, but also the thing that we're going to be doing the most, obviously. We can also use tables as functions. They're kind of limiting, right? But if there's no kind of summarized way to put this function out there, right? Then, or maybe if we have a small number of data points like here, right? Then we might have some function q which is g of n. So some function g takes an input n and returns q. And so that makes this n the input and q is the output. And I guess in theory, we will be the function g that does this work, or rather we'll use the table, which is the function g. Yeah. So for example, find, or I guess I should say, evaluate using the same terminology, g of 4. Nice. So here, n is 4, therefore q is 6. What if we have to solve g of n is equal to 7? Q is equal to 7, therefore n is equal to 3. What if I had picked 8 or 6? I would have had 2 outputs, or sorry, 2 inputs of n. Right, so I avoided it, but we can do it, and that's allowed. Okay, fine. Well, I'll do 8. How about? Q has to be 8, but if you span the Q's, plus you've got 2 of those, that's okay. Then n is either 1 or 5. That's allowed. Okay. Does each table represent y as a function of x? So remembering the rule about functions, so as long as each output only goes and generates, each input only generates one output, then it's a function. So let's see here. 2 goes to 4, 4 goes to 7, and 6 goes to 4. I'm kind of on high alert because I've got these 2 things, but that's okay, right? That's the same thing that we had earlier. So this is okay. How about the next one? No, right? Because, and I'll do it in red, I've got 4, an input of 4 mapping to 2 different outputs, 5 and 4. So it's not a function. And how about the last one? Last one looks good. 2 goes to 7, 4 goes to 5, 6 goes to 4. Cool. So if it's a function, we can't evaluate f of 2 if it's not a function, right? And so that's kind of the reason we have to check. We're going to evaluate f of 2 for both of these. I'll just do them down low here. F of 2, I give it an input of 2, and it gives me an output of 4. How about This one, same deal, 7. Evaluating, it's easy. Solving might be a little bit. So f of x is equal to 4 means that therefore x, now I've got 4 here going to 2 and 6, or I'll just write 2 or 6. And if f of x is equal to 4, I only have one output of 4, so that's cool. So the input, therefore x must be 6. Nice. What if we had to take it one step further? So we have to have a function in order for it to be one-to-one, right? But we already established that, okay, one-to-one is just kind of clean crossings, right? One output gives one input and one input yields one output. And so this first function here is not one-to-one, right? Because if I'm mapping back from 4, then I'm splitting and that's okay. It's going to 2 and 6 or 2 or 6. So the only one that's one-to-one here is going to be this last function, right? And so here, notice this function, oops, that doesn't, is also one-to-one. We have a vertical line test. So if you have a graph, or what we're going to be building up to is kind of being able to imagine these graphs, right? And so the vertical line test is just kind of a visual way to determine if we have a function. And so how it works is we draw vertical lines through the graph, right? Vertical, horizontal, vertical is this way, right? Because the horizon goes this way. I have to remember these things. Always have to kind of talk myself into it. Okay. And so if any vertical line would cross the graph more than once, then the graph does not define only one vertical output for each horizontal input. Right? And so the vertical line test, right, are any of these functions, guess I should introduce that, use the, I was gonna write VLT, but vertical line test. Now I'll introduce it, VLT, vertical line test, to determine which of the following are functions. So here, the first one, I'm just slicing and dicing, and I get these vertical lines, but they're only ever crossing the line at one point, right? And so this here passes the vertical line test. And so that means it is a function, because it passes the vertical line test. We already said that straight lines are functions, right? And the reason for that, or one of the reasons, is I can draw these kind of sloppy vertical lines at any point, and it's only going to cross the line at one 1 point. And so here, bink, also a function. How about these? Circles exist, right? That's fair. But they're not functions, right? We can still talk about them mathematically, and we have equations to represent circles. And so just the fact that it's not a function doesn't mean that it doesn't exist or that we can't work with it. It just means that makes it a little bit more difficult. And so this one, not a function, because it does not pass the vertical line test. We can build equations to represent circles, right? We can work with circles. One of the sneaky things that we could do is, what if I just consider the upper half and the lower half as two separate functions? And they're functions. That's allowed, right? So that's one of the kind of sneaky things that we do so that we can work with these still, right? But some things to think about. Horizontal line test. Maybe I'll do a little, so a vertical line looks like this, right? And a horizontal line looks like this. So once you have figured out that, okay, I have a function, then we might want to figure out if it's a one-to-one function, right? A special case of a function. And so then we can use the horizontal line test, right? And so then you draw horizontal lines through the graph. And if any horizontal line crosses the graph more than once, then it is not a one-to-one function, right? Thinking about the parabola that we saw, right? It's a function, but not a one-to-one function because it doesn't pass the horizontal line test. And so first, I'll eliminate this one because it's not a function, which means it's out of the running for America's Next Top Model. So it definitely can't be a one-to-one function. And maybe I'll say, are any of the previous functions one-to-one? So we had these two functions. So then what I do here, I'm feeling good, right? I'm only crossing once, but then it becomes pretty obvious that at some point, 1, 2, 3, that horizontal line is going to cross the graph 3 times, right? It doesn't matter. As long as it's more than once, it's not one-to-one. And so at that point, you can keep going, but you only need to find one to discredit the whole thing, right? How about this one? Finally, right, one-to-one function. Yay. This one passes the horizontal line test. Oh, bless you. 'Tis the season. Everyone's gonna get sick. It's like after summer, we all descend on this place. I affectionately call it a cesspool. because we're all coming from different places and we all bring our own flavors. My sister just got back from a wedding in France and she has COVID. The girl in the office next to me, she has COVID. Everyone has COVID. Not me yet. But if it happens, it's okay. Can handle it. Okay. Good. So this one, I guess I should passes the horizontal line test, therefore is 1-to-1. I guess I should say does not pass, or I'll just say is not 1-to-1. How about that? Okay. So now we've got these tricks up our sleeves, right? How do we figure out if it's a function? A function, we're going to use the vertical line test, right? Especially if we have an image like this, a graph, then that's going to be the easiest way to do it. We've seen tables, right? But now we're doing it visually. And which of these are functions? Boom, 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 boom. Boom, 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 boom. That one's good. Looks good to me. Bink. How about this parabola that's on its side? Uh-oh. Not a function. Still exists, clearly, but not a function. How about this little guy here? Gets dicey here at the origin, right, at 0, 0, but it's just ever so slightly going to be changing there. Well, funny you should ask. You'll have to wait until chapter 3. No, toolkit functions, which are today. We'll see. Now, how about this last one? Looks good, looks good, looks good. Uh-oh. Right. Just need to find one spot where it doesn't work, and then all of a sudden it's out the window. Oh, I guess I didn't do a bink. Can use graphs to do what we've been doing, right? So we started with the function written out and we evaluated and solved things using that function. And then we had a table representing a function. We evaluated and we solved. And now we're going to have a graph that represents a function and we can still evaluate and solve, right? And so we're doing the same thing over and over again with these different methods, right? But we're evaluating and solving back and forth. Let's see here. All right. How about I use kind of orange to do A, and I'll use, I don't know, light blue to do B, because otherwise it might get confusing. So if I have to evaluate f of 1, then 1 is the input, which is here, right? And I'm trying to find the output, which is this value here, which I can map back to roughly 3, right? We'll kind of squint a little bit. It's okay. So here for part A, f of 1 is equal to 3. Since an input, I'll just say it in words, of 1 yields an output of 3.
Like this squiggly equal sign. Like,
Yes. Approximately equal to. Because how sure are we? If we kind of go here, if I go up on this line here, oh, it's kind of shoved over, but let's see if I can. It actually doesn't really, if you really zoom in, I'm never going to be this picky. I'd be happy with 3, approximately 3, right? But kind of looks like not really. If we're going to be good about it. Approximately 3. It's okay if you said equal to, that's fine. Anytime you do any rounding, even if you keep a lot of decimal places, it's technically an approximation, right? And so if you give the decimal answer, you round it to even 5 decimal places, it's still an approximation. So you should use the squiggly equals, but we're never that picky, I think. Or I'm not. I am with myself, but not with you guys. What about the other way? Solving f of x equals 1. What's it asking me to do? It's asking me to solve for the value, the input, the x, that gives an output of 1. Yeah. And so here, I know that I have an output of 1, but notice an output of 1 goes to 3 spots, right? Goes to here, which might be easy to miss because I almost did. But also here and here. Okay. And so now we have 3 inputs, and I'll say approximately 0, -2, and -4. X is going to be 0 or approximately 0, -2, -4. Kind of easy when you use the graph, right? Any questions so far? No? Okay. Haven't been paying attention to my that's formulas are functions, right? I can give it some input, and I can generate some output, vice versa. And so if I have P as some output, right, then the function G takes an input of K, and what does it do to K? It squares it, multiplies it by 3, adds 1, Right, you always want to start at kind of the core of the onion and then work your way bloom out, right? And so k first gets squared, then multiplied by 3, then add 1, right? And so here I'll do g of k is 3k squared plus 1 says first take k and square it, then multiply by 3. Oops. Then multiply by 3, then add 1. I'll use the same kind of color scheme for A and B here. A, g of -2 means, okay, I've got 3k squared plus 1. So then I've got 3 times -2 squared plus 1. Order of operations say that I have to deal with brackets, exponents, division, multiplication are on the same level, right? Multiplication and addition are on the same level. When they're on the same level, addition and subtraction, I don't know what I said. When they're on the same level, you do them in the order that they appear from left to right. Yeah. And so, and that's BEDMAS, which might be familiar, or PEMDAS, if you're in the States, I guess. They use PEMDAS, parentheses, instead of brackets. We use BEDMAS typically. Has anyone not heard of BEDMAS? No. It's ringing a bell. All right. So in this order, so to show the order that I'm doing this work, right, I am going to use many lines, right? I encourage you to do the same. It's tedious, but kind of we're just warming up to math. So it's a good idea to just kind of highlight every step that you're doing so that you can backtrack later. -2 squared is 4, right? Any negative squared makes it positive, plus 1. So that's the first thing that I do, right? Then I multiply by 3, right? Take k and square it, done. Then multiply by 3 and then add 1. 3 times 4, I go with 12. Finally, plus 1 puts me at 13. So g of -2 is 13. Some notice 2 things. Oops. I stack my equal signs, bless you. So I don't want to see math written across the page. Very rarely will I do that if it's kind of, quick and easy math. And then I've got a page break coming up, right? But I want you to stack your equal signs, right? It makes reading your work for me, but also for you if you're looking back at it, or if you're sharing your work with someone else and they have to read it, right? It just makes it a lot easier to read. And so here we always stack the equal signs, stack our equal signs. What's another thing? I didn't bother writing anything on this side because nothing changed, right? So if something is unchanged, not only is it easier to just not write it, right? But it also indicates to me that, okay, this side, I don't need to pay attention to this side because nothing's happening here, right? And so kind of number one, number two, if there is no change on one side of the equal sign, we don't need to write sometimes I'll throw in, kind of remind myself, okay, g of -2 is 13 at the very end, but you don't have to. Okay? So that's just kind of good practice for math. Yeah.
In high school, the old physics, math, and science teacher told us that we could do like 2 lines, like vertical lines to the select this the same.
Yeah, so I don't need that because if it's empty, then, right, I just assume that it's staying the same. But yeah, you could draw a line down here, 2 lines, whatever helps to show you that nothing's changed. It's not until you need to reincorporate it into your math that you can reintroduce it, right? Okay. Good. So those are just kind of general math notes that I'll be using, but also expect you to use, right? Especially the stacking the equal signs. If there's no change, you're welcome to write g of -2, g of -2, g of -2, but you won't want to after a while. What about if we have to solve g of k is equal to 25? Well, now the input is the unknown, right? And so here, g of k, I do a little script k because otherwise it looks weird, is equal to 25. What we can do is we can say, okay, well, I can replace g of k with this function, right? 3k squared plus 1. So I can rewrite this as 3k squared plus 1 is equal to 25. Now, what I do quite often is I probably would have just used the equal sign as a revolving door, and I would have written 25 is equal to 3k squared plus 1, right? That's my preferred thing because I know 25 is just going to hang out for a little while, and I'm going to work with the 3k squared. I like working on the right-hand side of the equal sign, so a lot of the time I use that equal sign as a revolving door, and so just kind of switcheroo things. So, or, oh, I guess I should do it here. Or 25 is equal to 3k squared plus 1. That's the same. Convince yourself that that says the same thing. We can all agree. What am I trying to do here? I need to solve for k. Awesome. Solve for k. To shape k squared or even k on its own, we have to work backwards, right? And so then we need to work our way in towards the k. And so the first thing I need to do is I need to eliminate this plus 1, right? Which means I have to subtract 1 from both sides. I'm not going to show this probably ever again, kind of show the steps, but I'll do it today. 3k squared plus 1 minus 1, right? That's how I move that plus 1 to the other side. And so here, boom, boom. Now I have 24 is 3k squared. Right, plus 1 minus 1 makes 0, plus 0. 24 is equal to 3k squared. I want to get the k squared on its own, so I need to chip away that 3. How can I do that? I can divide both sides by 3. 3 divided by 3 makes 1. 1 times k squared. I don't even bother writing that. It's just k squared, right? And so that's how I'm getting it on its own. 24 divided by 3 is it 8? I should have just said it confidently. Thank you. I'm kind of running out of space here, so 8 is equal to k squared. So then, now I've got this k squared, and to get away from the square, I have to take the square root of both sides. But when I take the square root of both sides, I get plus minus. Right. Here's where I get extra crazy. What if I wrote k is plus minus square root of 8? What did I do? I used my revolving door again, because old habits. I like to have at the very end the thing that I'm solving for. I like to have it on the left-hand side, and I like to have what it is on the right-hand side of the equal sign. If you had written plus minus root 8 is k, then that's totally fine too, right? But what's the approximation here? Or k is approximately, what is the root of 8? 2 point, someone had it. 2.8, even.
No, 2.82847.
Good.
Wouldn't it just be better to write plus minus the square root of 8? Is
Mhm.
this an exact answer?
Totally. So this is the exact answer. This is an approximate answer. We're held back because your calculator only shows so many digits, right? It keeps going, right? And so that's why I use the squiggly equal to here. Awesome.
So when we're with the functions, maybe square or something, it's you always do the plus minus?
Yeah.
Always?
Yeah. Yeah, when you take the square root, it's always plus minus square root. A lot of the time what happens is the negative version doesn't apply, so then you can drop it, but then you'd have to say that. You'd have to tell me that. And then, so it's always plus minus.
How
And
would
then,
you know if it didn't apply? If you have the graph, or if you just want them all, what would you know? Is there a mathematical way to know? You're just doing this.
you, well, let's say the let's say the input is age. Can you have a negative age? No,
Okay.
right? So it would be one of those things, right? But yeah, that's like way ahead of where we're at. But that would be one of the examples is, okay, but I actually can't have a negative input, so my only answer is the positive one. But technically both. Awesome. Okay. Any questions so far? Okay. So I've glossed over, but mentioned a few times what we'll call the toolkit functions. Now, if we just kind of, I'm just gonna size this down just briefly. if I ask you, what shape is this? You'd say, oh, that's a triangle. What shape is this? So it's a circle. What's this even? Oh, it's a line, and I know the general equation of a line, right? Y equals mx plus b. So that's good. And so that's what we're going to build towards with these kind of core toolkit functions. And so we've got these, oops, toolkit functions. And the reason it's so important to talk about these functions in general is because if I know that, let's skip ahead to something kind of fun, x squared makes a parabola, right? I can do cool things like I can smush it, I can move it up, I can flip it on its side even. But knowing the general shape of x squared is going to help me visualize problems and just kind of adding it to the list of things that I know what they look like, right? And so I can manipulate x squared, but any function where the highest power of x is 2 is going to look like a parabola, right? Maybe like, right? Just kind of move it around. But if you see x squared plus x plus 3, parabola, right? I'll prove it. I'm going to be using Desmos
Yay.
quite a bit. So Desmos is a free app, and I use the graphing calculator, but also the scientific calculator sometimes if I need to show my work and take a screenshot and bring it in.
Ooh,
And so
love Desmos.
it's awesome. So if we have something like x squared, hey, there's a parabola. All right. What about if I add x? Okay, it did a little something.
Wait, what?
And then if I do plus 3, right? As long as the highest power of x is 2, it'll always be a parabola. What can I do? I could throw a negative in front. Right? But it's always going to have that same shape. Okay. And so that's why we're going to talk about these general shapes of these most common functions, these toolkit functions. Okay. Okay. Let's start with linear functions. Linear meaning straight line, right? And so you can have a constant function. That's pretty boring. Any input of x gives you just c. What does that look like?
A straight line across.
Just like that.
Yep.
Nice.
Wait,
So-
what if you added a negative to the c? But then it would go down. Never mind. I got
Then
it.
it's just. How about we have something a little bit more fun? The input is x, but the output is x. Then you've got this perfectly diagonal line. I guess I should add some fake axes here. Right? If the input is 1, the output is 1. If the input is 2, the output is 2. And again, we can manipulate x, right, to maybe have some slope m and some y-intercept b, mx plus b, right? And so, but at its core, there's just an x in there. It's got no power, well, power of 1, but that's boring, so we don't write it. About the absolute value of x.
Ain't that just always positive?
YMCA style. Taking the absolute value of a number, whoops, I need to make sure I do it properly. It's really hard to see, though. So the absolute value essentially drops the negative. We're going to talk about kind of the math behind that later, but for now, the absolute value of x, we're just gonna say drops the negative. That kind of hurts me to say, but it's true. Kind of, it's effectively what it does. Okay, so if you take the absolute value of -3, returns 3, right? So kind of the later half or the negative half of this straight line just becomes positive, right? So the absolute value. So far we've got some functions, right? We've got a straight line, we've got a absolute value, and we can build on these. We've already seen these power functions. Quadratic means that the highest power of x is 2, which is a parabola. So even for example, something like x squared plus x plus 3 or something like that still has that same shape, right? The highest power. The highest power of x is always going to look like a parabola. X to the 3. We'll use Desmos. Right? You can always talk yourself into something. X to the power of 3. Aha. I think you had a question. How do you generate something like that?
So inverse of that.
You could, I don't think I can
This
manipulate this,
would it be?
but it would be,
Yeah.
right? What would I have to do? I'd have to kind of invert it. How do I take the inverse of x to the 3? I take the third root. That's the graph.
You'd have to make it.
Yeah, I can't remember what that one looked like, but so the cubic we saw looks something like this. Little flare. The reciprocal. So now we're into these inverse functions. So 1 over x. What's the problem here? One thing I can't say enough is that we can't divide by 0, right? It's not allowed. You can't do it. You can ask your calculator to do it. It's going to clunk out. Well, it won't clunk out. It'll just say, oh, no thanks. So then what does that look like in graph form? In graph form, it yields an asymptote at x equals 0 in this case, right? Asymptote. Asymptote. So we have this asymptote at x equals 0 because we can't divide by 0. And then it just kind of has this, I don't know how to, ships in the night feeling, kind of like, woo. And so the reciprocal, I'll do it over here because we need a little bit more space. Is going to look like, we'll do it like in a different color maybe. And we've got an asymptote at x equals 0. One over x squared. We're just getting to know these guys. But, right, the square still makes it positive, but I still can't divide by 0 squared, which would be 0. So I still have that asymptote, but it just kind of flips that bottom guy. This little guy. you need to see my hand gestures for, I guess, but all right. So this I should have used different color for all of these. How about I cheat and go back and do it? Just tracing it in. The square root of x. Where's my square root of x? So notice in Desmos, they've got the x and the y's and the squares kind of ready to go, right? You can just use x and it'll assume that you want the x-axis. Root of x is going to be this kind of go starting at 0. And it's all positive. It's only when we move the other direction, right, from the square that we get plus minus. So it kind of looks like that. And then finally, the cube root. Oh, before, so the square root, can I take the square root of a negative number? No, right? It doesn't happen there, right? So that's another thing, right? We can't divide by 0, right? And we can't take the square root of a negative number. In fact, we can't take the even root of a negative number, but that's for later. Okay, so here, notice we can't take the even root of a negative number. Let's see if we can take the odd root, the cube root. I think there's some other functions in here, but I don't have a cube root button on here. So my shortcut is going to be x to the power of 1 divided by 3. Right? And that gives me the third root. Right? But there we have this shape that we were looking at earlier, right? Just like you said.
I know cubics can often have, when they're not in that form, they can go like this. What would be the cubic root of that? Would that still be a function?
Tricky question. Well, if it's like this, it would be x to the 3, some version of x to the 3, right?
Yes.
And so then it's a function. Just wondering if it's not necessarily 1-to-1. But then to undo it, yeah, you would take the third root. Okay. Let's see here. It's going to look something like, oh, now I can't remember. You're going to enter x to the 1/3 in your calculator or whatever. Okay. I'll leave the equation of a circle. Getting there. You can try it on your own before Tuesday. I will post an assignment on 1.1, which will include the equation of a circle. Okay, because we're almost done that, but you'll have lots of time to work on it. So I tend to give at least a week to do assignments. And so if you get to the circle parts, we haven't done them. You can try it though, give it a go. But so I'll post your first assignment and play around in Desmos. I encourage you to kind of get to know these little creatures, because it's really going to help when we're visualizing problems and just kind of imagining solutions as well. All right, with that, release you. I'll see you on Tuesday. Crazy.